Here's a question that seems simple until you think about it. You send a message. How do you know it arrived? In a face-to-face conversation, you know immediately. You can see the other person react. On a phone call, you hear yes, got it, thanks. Even with physical mail, there's a return receipt option, a card that comes back to you signed, confirming delivery. But on the internet, data travels invisibly across networks you don't control, through hardware you'll never see, to a destination that might be thousands of miles away. There's no direct feedback, no visible reaction, no automatic receipt. You send packets into the network, and from your device's perspective, they disappear. So how does your computer know whether they arrived? How does a file transfer know it completed successfully? How does anything work reliably on a network that makes no delivery guarantees? The answer is a mechanism called acknowledgement, and understanding it reveals something fundamental about how reliable communication is built on top of an unreliable foundation. Start with the problem in its starkest form. The internet moves data as packets, small, independent chunks, each one routed separately across the network. Any individual packet can be lost. A router along the path might be congested and drop it. A link might briefly fail. A hardware fault might corrupt it in transit. From the sending device's perspective, there is no way to directly observe whether a packet arrived. Once it leaves, it's gone. This is not a flaw in the internet's design. It's a deliberate choice. The network's job is to move packets efficiently, not to track every one. Tracking would require enormous state, every router maintaining records of every packet it forwarded, for every connection, at enormous scale. The internet handles billions of packets per second. That tracking is simply not feasible at the network layer. So the tracking responsibility was pushed to the endpoints, to the devices doing the communicating. If you want to know whether data arrived, your device has to find out for itself. And the only way to find out is to ask, or more precisely, to require the other side to tell you. This is the core of acknowledgement. The receiving side sends a message back to the sender, I got it. The sender, watching for these confirmations, knows what arrived and what didn't. Silence where a confirmation was expected means something went wrong. Let's trace exactly how this works in TCP, the protocol that implements reliable delivery for most internet traffic. When your device sends data over TCP, it doesn't just send raw bytes, it divides the data into segments and assigns each one a sequence number, a precise counter indicating exactly where in the overall data stream this segment belongs. The first segment might carry bytes 1 through 1460, the next carries bytes 1 through 61 through 2920, and so on. The receiving side, when it gets a segment, sends back an acknowledgement, a small message that says, I received everything up to byte number X, and I'm ready for byte X plus 1. This number, called the acknowledgement number, tells the sender precisely where the receiver is in the data stream. The sender keeps a running record, what has been sent, what has been acknowledged. Everything acknowledged is confirmed delivered. Everything sent but not yet acknowledged is in flight. The sender is waiting to hear back. If acknowledgement arrives, the sender advances and sends more. If it doesn't arrive within a defined time window, the sender retransmits, sends those segments again, assuming they were lost. This cycle, send, wait for acknowledgement, retransmit if none arrives, is the engine of reliable delivery. It runs continuously, invisibly, for the entire duration of a TCP connection. But there's a subtlety in this mechanism that's worth looking at carefully, because it reveals how much engineering goes into something that looks simple. The naive version of acknowledgement is, send one thing, wait for confirmation, send the next, one packet at a time. Completely reliable, you always know whether something arrived before moving on. Also completely impractical, because you're spending most of your time waiting rather than sending. Consider the physics. You send a packet to a server across the Atlantic. The round-trip time, your packet traveling there, the acknowledgement traveling back, might be 80 milliseconds. If you wait for each acknowledgement before sending the next packet, you can send at most 12 or 13 packets per second, regardless of how fast your connection is. That's extraordinarily slow for a modern network. TCP solves this with a concept called the window. Rather than waiting for each packet to be acknowledged before sending the next, TCP allows multiple packets to be in flight simultaneously, sent but not yet acknowledged. The number of packets that can be in flight at once is controlled by the window size. With a large window, the sender can keep pumping data continuously, filling the available bandwidth, only pausing when the window fills up, when there are so many unacknowledged packets in flight that sending more would risk overwhelming the receiver or the network. Acknowledgements, as they arrive, slide the window forward, freeing up space for new packets to be sent. This is called a sliding window, and it's the mechanism that makes TCP fast despite the round-trip overhead of acknowledgements. You get continuous throughput without giving up the reliability guarantee. Now let's talk about what happens when something goes wrong, when the sender is waiting for an acknowledgement and it doesn't come. The sender has a timer running for every segment in flight. If the timer expires before the acknowledgement arrives, the sender declares that segment lost and retransmits it. This is the retransmission mechanism, and it's what gives TCP its reliability guarantee. No matter how many times a packet is dropped, TCP will keep retransmitting until it either receives confirmation or gives up entirely and reports a connection failure. But there's a tricky question buried here. How long should the timer be? How long does the sender wait before deciding the acknowledgement isn't coming? Set the timer too short and you retransmit constantly, sending duplicate data, wasting bandwidth, flooding the network with redundant packets for data that actually arrived, but whose acknowledgement was just slightly delayed. Set it too long, and you wait unnecessarily after a real loss, introducing large gaps in transmission while the timer counts down before retransmission begins. The right answer depends on how long acknowledgements actually take to arrive, the round-trip time between sender and receiver. But that round-trip time isn't fixed. It varies with network conditions, congestion, and load. A connection that has 20 millisecond round trips normally might see 150 millisecond round trips when the network is congested. TCP measures the round-trip time continuously, timing every acknowledgement as it arrives, tracking how long segments are taking to be confirmed. It maintains a running estimate of the expected round-trip time and sets its retransmission timer dynamically, based on that estimate plus a margin for variability. When the network slows down, the timer extends automatically. When it speeds up, the timer tightens. This adaptive timer is one of the more elegant details of TCP's design. It's self-calibrating, continuously measuring the network it's running on and adjusting its behavior to match. There's one more piece of the acknowledgement picture that's worth understanding, because it explains a behavior you've probably observed without knowing why. What happens when packets arrive out of order? Suppose the sender transmits segments 1, 2, 3, and 4. Segment 3 takes a slightly different path through the network and arrives late. The receiver gets 1, 2, 4, and then later 3. When segment 4 arrives before segment 3, the receiver doesn't immediately deliver it to the application. It holds it in a buffer, waiting for the missing segment 3 to fill the gap. Meanwhile, it sends a special acknowledgement, a duplicate acknowledgement that says, "I've received something beyond byte X, but I'm still waiting for byte X itself. I know something is missing." When the sender sees multiple duplicate acknowledgements, it doesn't wait for the retransmission timer to expire. It takes that as a strong signal that a specific segment was lost and retransmits it immediately. A mechanism called fast retransmit. The missing segment arrives, fills the gap, and the receiver can now deliver segments 3 and 4 to the application in order. From the application's perspective, nothing unusual happened. Data arrived in order. The out-of-order delivery, the buffering, the duplicate acknowledgement, the fast retransmit, all invisible. TCP handled it entirely transparently. This is the broader pattern of everything we've covered. The unreliable network delivering packets that get lost, delayed, duplicated, and reordered. And TCP, through sequence numbers, acknowledgements, timers, and retransmission, converting that unreliable substrate into a reliable stream that applications can trust completely. When you download a file and it arrives perfectly intact, this is why. When you submit a form and the server confirms it received your data, this is the mechanism underneath. When a chat message is marked as delivered, some version of this acknowledgement cycle has completed successfully. The network doesn't promise your data will arrive, it never has. What TCP provides is a layer on top of that honest, unreliable network, a layer that watches every byte, notices every gap, and fills every gap before passing data up to your application. Reliable delivery on the internet isn't magic. It isn't a property of the network. It's a protocol running at the endpoints, doing the careful, continuous work of confirming receipt and refusing to move on until it gets confirmation.